For the rest of our videos, we're mostly going to be studying specific NP-complete problems and showing that they are NP-complete. Our first one is going to be Boolean Satisfiability. This sounds very fancy, it's a very easy statement. Given a Boolean expression such as this, can I assign true and false to the variables such that it is true? Very simple question. Can I satisfy that Boolean expression? This is proven to be NP-complete by Cook's theorem. It's well beyond the scope of this course to prove that theorem. What we're going to do is look at a slightly simpler problem. Let's start with some definitions that you may or may not have used in Foundations 1, so it's worth looking at them. Here, we're going to say a literal is a Boolean variable, either xi or xi bar. Xi bar is the notation I am using for the negation. This is the negation of xi. So a literal is either a variable or its negation. A Boolean clause, or sometimes called a disjunction, is a bunch of ors of literals. So it's x1 or x3 or x4 or. That is what a Boolean clause is. The reason we talk about these is we want to be able to write things in a consistent way. There's a lot of logical operators, as you likely learned in Foundations 1. We want to use as few as possible. It's not quite true, but we don't want to use too many of them. So we're going to write things in what we call conjunctive normal form, which is a very large phrase for a very simple idea. All of our expressions are going to be ands of ors. So we're going to have a bunch of ors, and a bunch of ors, and a bunch of ors. This is called conjunctive normal form. Now we can try to reason through our analysis in this form. And this seems like a very convenient form because you can look at each clause and kind of analyze it on its own and say at least one of those has to be true. Then at least one of these has to be true. And then at least one of these has to be true. And you can analyze it in somewhat of a consistent manner. So this seems like a very reasonable thing. This is called conjunctive normal form. We will mention that there is an easier form, which is called 3CNF, which is an and of Boolean clauses where each clause has exactly 3 literals. Very straightforward. Just limit yourself to having 3. In fact, you're always going to ensure you have exactly 3. A truth assignment is choosing true and false for those literals. So let's do that. We're going to analyze what this truth assignment evaluates to for this expression. So let's see if we had x1 is true, or x3 is false, so not x3 is true, or x4, which is false, and x2, not x2, or x3, or not x4, and not x1, or x2, or x3. Well, this is going to be true, and true, and true, so this is equal to true. So this truth assignment satisfies this Boolean expression in 3CNF. Which now you sound really fancy for just saying, yup, it's true, but these are the words we're going to try to use to be mathematically consistent in our analysis. Next, we have an expression. I want you to try to come up with a truth assignment for this expression. I'm going to keep talking, and to make sure that you actually pause the video, try and come up with something to assign these variables to make that statement true. All right, hopefully you did that. Now, having done that, let's check some that work. So one way you could do this might be, I notice x3 appears in 2 of them, so why not set x3 to be true? And then I just need to make any assignment to make this last one true. I could either make x2 equal to true or x4 equal to false, and that would work. So if I did x3 equals true, x2 equals true, I actually have 2 variables that don't matter. x1 could be false or true, and x4 could be false or true, which is kind of neat. And there's many more truth assignments for this particular Boolean expression. So this seems relatively straightforward, that finding a truth assignment that satisfies a Boolean expression is NP-complete. So let's actually analyze this in a bit more detail. We're going to simplify our analysis to the 3-sat problem. The Boolean satisfiability problem is called the sat problem for satisfiability. And here we're going to look at an expression in 3CNF, and we're going to ask, can it be satisfied? Very simple question. First, we're going to prove that it is an NP. NP means that you can verify it in polynomial time. This is always important. I'm going to write this in big letters here. All you need to do is verify an answer. That's all you need to do. You do not need to solve the problem. All you need to do is say, if someone came down from on high and gave me a solution, can I at least check that they weren't lying to me, that it was in fact a solution? I gave them very mathematical proof here, which is, well, 3sat is definitely a subset of satisfiability because it's just a particular type of Boolean expression, so it's definitely an NP. You could just say, give me an algorithm, and explain how you could use that algorithm to verify the solution in polynomial time. And that's the one important thing you got to make sure you do, is that you say in polynomial time. All right. So this is the easy part typically. It's just check the answer. Almost always you just need to do a brief description. We'll see several of these later for how can you prove something is an NP. Just explain to me how you check your solution. I wanted to give a very mathematical example here to show you that you don't always need to even say how you verify it. Next comes the tricky part, which is I need to show that this thing, 3sat, is NP complete. How could I do this? So the thing I need to prove is, given any problem in NP, I can reduce it to 3sat somehow. How could we do that? Well, it's not obvious, but we do know one thing, which is I can take the following step. I can reduce any problem in NP to sat. Because of Cook's theorem. We didn't prove it, but assuming that Cook's theorem is correct, which it is, we can make this reduction. Beyond that, so if we can reduce sat to 3sat, then we can do this reduction. We just do them back to back. I rewrite the problem in NP in terms of sat, and then I rewrite sat in terms of 3sat. And if both of those take polynomial time, polynomials are closed under composition, so this dual composition will leave me with a polynomial. Potentially a higher degree polynomial than I could if I made the reduction directly, but that doesn't matter. All we care mathematically is that I can somehow reduce these problems to these problems. So we're narrowing our vision into proving the following reduction from sat to 3sat. Remember, a reduction is give me a sat problem. I will rewrite it in terms of a 3sat problem, and I need to be able to do that in polynomial time. So what I'm actually doing here, I'll write my actual proposition next to this, is reduce sat to 3sat in polynomial time. And all of our propositions going forward will read mostly like that. We'll say take this problem and reduce it to this problem. That is enough to show that it is NP complete. For our proof here, I'm not actually going to go through all of the details. It's very tedious. I will provide you guys with a link to a full complete proof if you want it. It's mostly describing the process we do here in some brutally over-the-top explanations. So, given a CNF formula, not necessarily 3CNF, we must find an equivalent 3CNF expression. Notice, all we care about is that the first one is satisfiable if and only if the second one is satisfiable. They don't even need to have the same variables. You could rename every single variable and do a whole bunch of other nonsense and allow this to still work. So, what we're going to do is take phi here and rewrite it in terms of other variables potentially and call it psi, and that new variable psi should be satisfiable only if the original is. So, why is this expression I gave you not in 3CNF? Hopefully you can find it pretty quickly, because 3CNF meant that there was 3 in each of these clauses. This last guy ain't got 3. So our problem is this expression over here. So let's narrow our vision into that expression. So this causes a problem. Let's write that. That's a problem. Let's see what we can do. So we're going to try to rewrite that. x1 bar, x2 bar. So it's x1 bar, or x2 bar, or x3, or x4. What I want to do is, let's do something simple maybe. I'm going to keep the first two variables as is, x1 bar or x2 bar. And then I'm going to say or xa, where xa is what I'm going to call those two variables. Those are the same. So maybe I'll color these in a different color. I'll color this as black, and I will get rid of the highlighter. Let's maybe do this to format it nicer. Style, red, and then style, red. But I can't just do that. What I'm going to do instead is I'm also going to say what xa is. I have not defined that variable, so I need to do and xa is true if and only if x3 or x4. So I'm saying this expression over here is saying that xa is exactly the same as x3 or x4. I just need to write that out somewhere to verify that the assignments line up exactly. But now I have a bigger problem potentially, which is this is not an and or an or. It has three variables, funny enough, but it is not and or an or. So let's try and play with it. I can rewrite an if and only if in terms of two implications. So I'm going to write this as x1 bar or x2 bar or xa, and I can write that second thing as xa implies x3 or x4, and xa is implied by, maybe we don't write it that way because that symbol most people don't like, so let's write it instead as x3 or x4 implies xa. So that is our substitution. Now, flashing way back to maybe week 2 of Foundations 1, you need to remember what an implication is and how you can rewrite it in terms of ands and ors. So I can rewrite this as x1 bar or x2 bar or xa, and that first implication, if you remember, P implies Q is the same as not P or Q. So I can write that as xa bar or x3 or x4. This is not the first part of the implication or the second. Now, the second one is x3 or x4 bar or the second. And now we need to use our good old friend De Morgan for his laws, which say how you negate an or. So we have these first two terms now look good. It's an or of three things and an or of three things. So we just got to deal with that last one. This is x1 bar or x2 bar or xa, and xa bar or x3 or x4. And for this last expression, we have x3 or x4 I can rewrite as x3 and x4, both of them negated, or xa. And now the only problem that's left is this last term here. And if you remember your distributive laws, we can make some progress here. So let's say this is equal to x1 bar or x2 bar or xa, and xa bar or x3 or x4. And I can distribute the or and write this as xa or x3 bar and xa or x4 bar. And now we're so close. We have three literals, two literals, two literals. So for these last two terms, let's copy paste so we don't need to copy down all of this. For those last two terms, what we're going to do is a very simple thing. We're just going to snag this, move it over. Nope, can't do that. Undo. What we're going to do is we are going to take this to literal term and just or another one of the variables again. So I'm going to or xa. That's it. Just add on done. Now we have 3 variables in it. Then we can do and xa or x4 bar or xa. And now I've taken that expression that had 4 literals and rewritten it as 4 clauses that all have 3 literals. So I have this expression I would need to substitute in for that original clause up there. And then I will have rewritten phi in terms of a new Boolean expression called psi that is in 3CNF, and they are exactly the same. That's what all these equalities mean. So I will have successfully transformed sat into 3sat. Notice, this is not a generic proof. I just did an example. Again, for this, if you want a generic proof, you're going to need to look that up. I can provide you a source if you want. It's just a tedious process of explaining this algorithm I just went to. There was nothing special about what I did for the fact that these variables were named what they were. Anytime you had 4, you could do it this way. Anytime you had more than 4, you can just do this process inductively. And that is effectively what the proof does.